Check. So good afternoon, students. We are actually solving this particular problem in our last lecture. It's in the morning. Now let's write this here. Q total we have Q for 159 mm. You have it as 12.44 watts, and Q for 80 mm. It is 9 watts. Also, you got Q for tip insulated case, and this total is 14 watts. And here you also got Q for 80 mm. Q for 80 mm, you got it as 9.31 watts. Here you got Q total, which is 11.03 watts. Okay. So what I want to do is I want you to look at all these numbers. Okay. Look at the numbers. And based on the numbers, you should be in position to decide which one will you take. Okay. Whether you for the required case. Okay. Let us say you are designing a fin real time. Okay. When you're designing a real time fin, this is how you should be choosing your fin. Okay, first you will tabulate the results in various cases, finding it out analytically. Once you find it out analytically, when you put all these things in front of you, you will understand which one will be the best case based on your situation. Okay, see, if you want the temperature to be as least as possible, you will go for this case. Okay, in this case, you have least temperature among all. Okay, if temperature is not the important issue, you will go for this case. Okay, it is based on this. But among these two, if you have to choose, which one will be you choose is depending on a trade-off. See, here you have 106 degrees centigrade, and here you have 98.7 degrees centigrade. So it is nothing but, the difference is almost 8 degrees centigrade. For 8 degrees centigrade, you need not keep adding the material for, if this is 80 and the whole length is 159, halfway is 80 and the remaining 80, if you add, it will be 160. That is almost 159. So if you add 159, that is, this is 50%, this is 50%. For 50% increase, you got only 10 degrees. Okay, difference. So the 10 degrees it has reduced. So this you can actually neglect. Instead of taking this, this will be a better preference for you. Okay, so based on the situation, you have to look at and take it. See, even here, if you look at these q values, okay, in the first case you have 14, right? But in this 14, no, the whole thing is taken care in the 80 itself. Most part of it is taken care in 80 itself. The difference between these two is very small. Okay, it is just 3.4 watts. Okay, if we increase 50%, how much it is increasing? Only 3 watts is increasing. So based on the volume of material used, where volume of the material used, you will actually decide upon the size of the fin. Actually, it is not just the q value, t value, but based on the volume of the material that you are going to use, you have to decide in reality, because that will escalate your cost. Okay, it is not just the performance that is required, it is also cost that matters. So keeping these things, you will get something called as a trade-off. Once you get this trade-off, you'll be in position to actually decide which one is the best that will suit your case. Okay, let's move on. When we move on, we'll have to see something called as effectiveness of fin. The next case we will take effectiveness of fin. This is one important parameter or a performance parameter of a fin. So if I have to define the effectiveness, it is written with epsilon. Effectiveness of fin is, if we want to define it, Q that is happening in fin versus the Q that is there without fin. That is Q fin versus Q no fin. Uh, if you want to calculate Q fin, it is nothing but efficiency of the fin into the Q max by Q no fin. This is the you know uh, way of expressing it. If you want to you know reduce it to the general terms, introduce what is the Q max is. Okay, Q max is nothing but Q convection. So Q convection is H into A into delta T, that is P into L into theta naught, I can say TB minus T infinity. Q, when there is no fin, it is H into area, and this area I can call it is like area of the base itself, because there is no fin now in the denominator case. Okay, I'm just writing the area into the theta, the same theta naught I'll have, so that I can cancel this theta naught, HS goes. So what to get here is efficiency of the fin into P into L. I'll write it like area that is exposed to the atmosphere through the fin, that is the area of the fin by area of the base. So simply put, effectiveness of fin is actually written like this. This is one important formula which you must remember. Sometimes it is asked in the questions. Now, let's move on to this data book. See, in this data book, page number, right, the data book in page number 58, we're actually looking at this extended fins or surfaces. So here, these cases we have seen. Okay. So the third case, the 1, 2, 3, 1, 2, 3. This is fourth case. This I am leaving it to you. Okay, you can solve it for yourself. It is like this one only, the extended case of this third case. You can do it for yourself. You can take out a problem from any given textbook and solve it. So in this particular fins, we have solved problems for all the three cases. Okay, in all the three cases, there can be different kinds of problems wherein efficiency is asked. Here it is 1 by ml. Here it is this one. Here uh, it's actually it can be derived from these two. Okay, using these two, you can have it here. Or simply, what I suggest you is you first find out this one. Okay, because the what is efficiency of the fin? It is Q by Q max. So what is Q? This is Q. This is Q. You can find out Q using this. Once you have the Q with you, you can find out the Q max. What is the Q max? The Q max is equal to the H delta T simply. Okay, when this is at TB minus T infinity, you'll get Q max. So simply you can solve this one also. Okay, so we have completed this part, these three cases of our fin. Okay, these three cases of our fin we have completed. Now let's move to the next page. Okay, here what you will have is it's a circumferential or rectangular triangular fins. Okay, so if it is circumferential, you will have to use this side box. If it is rectangular and triangular, you have to use this side box. Right? So it is in page number 59. You may refer to your data book. All these things are given in your data book. Now, let us solve problem based on this concept. Okay. This is square actually. Okay. Here you have determined the heat flow for rectangular fins and the triangular fins for 20 mm length. 20 length is given in question, and 3 base is given. Thermal conductivity is given as 45 watt per meter Kelvin, and the heat transfer coefficient is 100 watt per meter square Kelvin. So the K is 45 watt per meter Kelvin, and H is equal to 100 watt per meter square Kelvin, and TB is also given. The base temperature is 120 degrees centigrade. This is given. Surrounding fluid temperature is given. That is T infinity is 35 degrees centigrade. Okay. What he's asking is he's asking determine the heat flow. What is the Q value? Also, he's asking effectiveness of fin. Okay. Now let's move on to this one. Okay. Say if you look at this particular thing, okay, I'll zoom it here. You can see this he's calling it as length. Okay, and this he's calling it as thickness. So according to his nomenclature, this 20 is L, and this is thickness. Okay, so let's do it for the rectangular fins in the first place. We have rectangular fins now. Here you have to use the line below, okay, the curve below. This is for rectangular. As you can see, this is a rectangular shape that is given on, and this is a triangular shape. Okay, now if this is rectangular, first you should get what is the x-axis value. Okay, this particular expression that is there here, you have to actually get the value for it. It will vary between 0 to 3. Okay, it will vary between 0 to 3. So what you will do is you will go to this, and it is page number 59. In page number 59, you will have the x-axis and y-axis. This is the thing. On x-axis, what you have is On x-axis, what you have is LC. LC is equal to L plus T by 2. Okay. So L is given in question as 20 mm. That is 20 into 10 to the power of minus 3. And T is given as 3. So 3 into 10 to the power of minus 3 by 2. So tell me what is the value of LC? Let me move to problem. LC is
0.0215.
215 meters. This will be your LC. So done with LC, this one. And the next thing is H. H is given in the question, so you need not worry. So the next thing is K. K is also given in question, you need not worry. AM is required. AM. So for finding out AM in your data book, the formula is T into LC. Okay. The T value is 3 mm and the LC value is 0.0215. Now you got AM value. Tell me what is AM now?
6.45 to 10 power of minus 5.
10 to the power of minus 5. Okay, this is your AM. See, what you wanted to calculate is actually LC power 1.5 into H by K into AM whole to the power of 0.5. This is what you want to calculate. And the LC value, you know it as 0.0215 into the H value is given in the problem. It is given as 100, isn't it? Yeah, it's given as 100. And the K value is given as 45. The AM value just now we have found out, it will be in meter square 6.45 into 10 to the power of minus 5 power 0.5. Okay, this is what you have it on x-axis. Now tell me what is this value?
0.58.
0.585. Okay, this is what you got on the x-axis. So the x-axis value is 0.585. And you have a curve like this. So what you have to do is you have to find out the efficiency that is on the y-axis. How to find out is you will find out using the graph itself. Okay, you will point out this point 0.585 on the graph, and you will take it vertically, and then horizontally you will move to the y-axis. When you move horizontally to the y-axis, you will get that. So let me show it here. 0.585. That's what we got it, right? So 0.585 will be somewhere around here. Okay, it's almost near to 0.5. Okay, so this is the line. So here I will get it. Somewhere over here I'll get it. So if I will take it on the x-axis, what will be this value? This will be greater than 80, and this is 90 here. It is less than 90. So it is around 0.82 like that. Okay, 8382 you can take. So is it clear? I hope it's clear. So what you get on this one is 0.82. Okay, so that is how you get the efficiency. What is the use of getting this efficiency? Okay, I will write it here. From graph, the efficiency is 0.82. That's what you got. And on the other side, what is the use of this efficiency? Okay, see, actually in this particular graph itself, this page itself, he has given this formula. Can you see this formula on the top? The Q formula is actually expressed in terms of efficiency. Okay, so using this, you have to find out what is your Q actually. So your Q is equal to efficiency into AS into H into TB minus T infinity. Okay, so in this one, you have efficiency with you, H with you, TB by T infinity, all the things are there. AS is not there. AS also should be found out. For AS also, he must have given some clue in your data book itself. So where is it? See here, can you see this? This is the AS formula. AS is equal to 2LC into the depth. That's what is given. Okay. AS is equal to 2LC into the depth. Okay. 2LC into the depth. That is a formula. You will get it from the data book again. Okay. From page 59, you'll get this. So in this, you have this is equal to 2 into LC is 0.0215. And the depth, what is the depth that is given in question? Is depth given in question? The base is given here. Base is 3 mm is given. Can you take this as depth? See, that is not the depth actually. Okay. If you have a fin like this here, okay, this is actually 3 mm, but depth is this one. I hope you are getting what it is. Okay, this one you need. See, if it is not given in question, what I have to do is you have to take it per unit depth. That is 1 meter. So you substitute 1 here and get this AS. Tell me what is this AS now? 0.043 meters square. That is your AS. Now you can simply substitute these things into your Q. The Q is equal to the efficiency value. Just now you got it as 0.82, and the AS value you got it as 0.043, and the H value
299.3.
what? 99 somebody said. Okay, the H value is given as 100, and the TB minus T infinity, it is 120 minus 35. Tell me what is this value now?
299.
299,
9.7.
9.7 watts. Okay. Okay. Since you have taken depth as 1 meter, you can write it like per unit depth. See, whenever you are assuming something, it is better to put that one in units itself. So the Q value for unit depth is this one. Okay, this is actually one way of finding it. Actually, see, you can also find out this particular value using the formula that you have in the data book that we have used previously. See, whatever the case that you have used here is simply like the second case here. Yeah, this case. Okay, let's cross check this one with this case. Okay, it is root over HPKA. Q is equal to root over HPKA into TB minus T infinity into tan H M. So the H value is given as what? It is 100 given in the question. The P, if you have to calculate, you are considering it as 1 meter. Okay. So if it is 1 meter, you will have 2 times of that 1 meter plus the thickness. The thickness is given as 3 mm, 3 into 10 to the power of minus 3 have to put. And K value is given in question and its value is 45 into the A area perpendicular to the direction of heat transfer. It is like again thickness, that is 10 to the power of minus 3 into the other dimension in this one, it is 1. Okay, so you will get that. That is area into the TB is 120 minus 35 into tan H, the ml. So m, I am writing it as a root here. The same things you will get here, 100 into 2 into 1 into 10 1 plus 1 plus 10, 3 into 10 to the power of minus 3 by 45 into 3 into 10 to the power of minus 3 into 1. Okay, into L also will be there. The L value here is 20 mm. So L is 20 to 10 to the power of minus 3. The substitute, you will get the Q value. Tell me what is this Q value? See, this Q value will be somewhere near to your 299. What? 280, yeah?
286.19 watts per minute.
286.19 watts. Okay,
So
this is
just
almost near to 299 watts. So whatever you have found out using the graphical method, this is actually analytical and this is graphical. Okay, so the graphical is giving you a closed result. Okay, that is fine enough. Okay, so that's what I would like to convey by doing this. Also, he's asking you to find the effectiveness. Okay, how do you find out the effectiveness? Effectiveness is actually the efficiency of the fin into area of the fin by the area without fin, or area of the base you can write. Okay, so the efficiency of the fin I have just found out, it is 0.82, right? 0.82, and the area of the fin, when I say area of the fin, it is again the 2 times of I'm writing the perimeter first here. 2 times 1, that is A. The other side is 3 into 10 to the power of minus 3 into 1. That will be the area of the fin. Perimeter into length. And the area in the denominator will be like 1 into 3 into 10 to the power of minus 3. So now you tell me what is the effectiveness formula. What is the formula? What is the value? Did you guys calculate? Somebody please calculate and tell me what is this. See, since this is effectiveness, it can be like any value, not like efficiency, which should be less than 1.
Is it 548? 548.3.
548. No,
548.3.
548. No, that much it will not be there. No,
Sir, for area type guess perimeter.
yeah, perimeter into length I have taken. This is perimeter.
Okay.
This is length. Perimeter into length is area.
Okay, sir.
You are getting only 543. Hmm? Tell me what is the value you are getting.
548.3.
I don't think this is right. Effectiveness, let us calculate by the Q formula.
54.83.
54.83. Yeah? Okay, whatever value we get. Let's keep it aside. This particular discussion. Let me do it with this from the basic formula. Q fin versus Q no fin. This you will do. So the Q fin you have it with you just now. It got it as 299. Okay, you want how to calculate Q without the fin. Okay, Q without the fin, that is like HA delta T, TB minus T infinity. So that is 299 by the H value is 100. The area value is the length into thickness. Length is 1 and the thickness is 0.003. That is 3 mm into TB minus T infinity. That is 120 minus, what is this? 120 minus 35. 120 minus 35. Please tell me what is this effectiveness now?
11.72.
11.7.
11.7. So you follow this one. This is more reliable. Okay. Maybe we are missing tan HML here. That is the reason why you got a different value here. Anyways, this formula you follow it for the long fin case. That will be more productive. This you follow for each and every case. That will be a good help to you. Okay. Anyways, let's move on. Yeah. Here, what we have done so far is we have solved only for the rectangular fin. That is first case we have solved so far. The triangular fin also we have to solve. Okay. Let's move to the triangular fin. The same problem. In the second case, you use triangular fin. What is the triangular fin? Again, for the triangular fin, what happened? Yeah, you have to triangular fin. See, for whether it is a triangular fin or the rectangular fin, the x-axis value is same. The x-axis expression is same, but LC and AM are varying. Both the cases. So you have to do it again actually. See, that is equal to L again. That is 0.0214, right? Is it right? No, no. The L is 0.0214. And the next case is AM. Is the thickness 3 into 10 to the power minus 3 by 2 into the L is 0.02. So tell me what is the AM value?
3 into 10 power minus 6. No, sorry, it's 10 power minus 5.
Please repeat it. Somebody is talking.
3 into 10 power of 5.
10 power minus.
They are saying something but not audible to me.
3 into 10 power of
3
minus
into 10 power minus
Power of minus 5,
5.
right? Meter square. Okay. Now, moving to this one, this is 2 into LC. LC is nothing but L here, 0.002 in our case. No, 0.02 into the depth. Anyways, you will take it as 1 because it is not given in the question. So tell me what is AS?
0.04.
0.
0.04 meters square. Fine. So done with everything else. What you need is you need to find out actually this LC into this whole term. So if I have to do that, you put it LC power on 0.5 by H power H by K into AM for the power of 0.5. And the LC value, you have it as 0.02. The H value is 100. The K value, what it is? 45. And the AM value is 3 into 10 to the power of minus 5. Whole power 0.5. Okay. So you tell me what is this x-axis value?
0.769.
0.769 is your x-axis value. So here, what you will have for this one is you have a curve like this, and this curve is for triangular one. Again, we are on page number 59, and what is this? 0.7.
769.
that is your x-axis value. Corresponding to this, you will have some value of efficiency on y-axis. Okay, this is almost 0.77. If I have to take 0.77 from this, I'll have to take it somewhere over here, because this is 0.75. Somewhere near to this, you will have a curve. The triangular fin curve is on the top here. So if I add it here, I get the efficiency. Okay. What is the efficiency? This is 1 less than 80. So what you get is 0.79, 79% you will get. So approximately you can take 0.79. So efficiency you got it as from graph the efficiency is 0.79. What is the next thing to do? You have to find out the Q. You know the Q formula is given in this one. It is on the top here. The same Q formula, we will put it here. Q is equal to efficiency into AF into H into TB minus T infinity. This formula I have written it here. Okay. So now tell me what is the efficiency? It is 0.79. And the AS just now we have found out. AS value is here. That is 0.44. 0.04. So the H value is given as 100 in the question, and the TB value is 120, and the T infinity is 35. So tell me what is Q?
268.6.
268 point.
68 point.
Sir, 268.
268.6 watts. That's how you will get the Q value. Next, you find out the effectiveness also. He's also asking you to find out the effectiveness. So, how to find out the effectiveness here? We'll follow the second procedure that I told you just now. Effectiveness is equal to Q by Q no fin. Q fin by Q no fin. So, the Q fin is the value that you have got just now, 268.6. And the Q no fin is HA into TB minus T infinity, that is 268.65. The H value, you know, it is 100. And the area is 0.03 is 0.003 is your thickness. And then the length is given as 1. This will constitute area. And the TB minus T infinity is 120 minus 35. So tell me what is the effectiveness?
10.5.
10.5
5.
is your effectiveness. And the effectiveness will not have any unit.
Sir, here area triangle, no, sir.
See, area is triangle is the question. Okay, that's very good question. See, here this is a wall. This is your, triangular fin. But here, when I consider area, I have to consider something like this. have something like this also. See, what is the area essentially here? This is the area. Okay, so this is 3 mm and this is 1 meter. So if I want it, it is 3 mm. This 3 mm into 1 meter. Okay, is that clear? Whoever is asking this question.
Yes, sir.
So area without fin, if you write, this area will remain. That is 3 mm into 1 meter. You have to write. Hope it's clear. Now, see, let us discuss little about this result. Effectiveness and Q. First, you have a rectangular fin, and then you also have the triangular fin. These are the things, and then you have Q in both the cases, and you have effectiveness in both the cases. What is the Q that you have got in the first case? 296 point something. And then here, 299.
Oh,
Triangular, what is the value? 268. The effectiveness here, it is 11.61. Here it is 10.53. See, you compare these two now. The effectiveness is high here, here it is low. Okay, based on effectiveness, if you have to choose your fin, you will obviously choose this one. But in reality, people will not choose this one. People will choose this one. Okay? The triangular fin is chosen because you will have something called as volume. Okay, if you consider the volume, here the volume is very high and here the volume is very less, because it will save a lot of volume. Maybe 50% of the volume will be saved. Okay, when it is saved now for at an expense of one one unit of effectiveness, you need not use this much of material here. That's why people will go for this one itself. Okay, so I hope it's clear to you.